Hello and welcome to this tutorial. In this one, we're going to be looking at the assignment graphing motion. Let's begin. In this activity, you'll use the graph of the motion of a car to determine its velocity and starting location. You will then try to predict the location of the car at some future time that is not shown on the graph. You will assume the car has continued to move at a constant rate. Okay, enter your name. Let's begin. Well, the very first thing we need to do, guys, we need to find the slope of the car. The slope of the line, because the slope of the line is the speed of the car. So we need to find that first. So remember, slope is rise over run. Okay, now go ahead and start at the bottom of your line. Okay, now you can see your starting position is just a little bit less than 200. So I'm going to call my initial position x naught a little less than 200. So I'm thinking, I don't know, 198, 199. It's going to be a little less. So I'm going to go 198. Okay. Now, as I work up the line, I'm looking for where the line crosses through the exact corner of the box. Well, I really like that point. Let me see so I can help you reference this. Okay. So at the bottom, you can see that there between 0 and 5, there are 10 little marks. Okay, that means each little mark, since there's 10 of them between 0 and 5, has to be 0.05. So that big mark in the middle between 0 and 5 would be 2.5, right? So 2.5. So if I go up 2.5 all the way to where it intersects the graph at 230. So 2.5 and a position of 230. 2, I'm going to keep going up. And really not too far away at 4, a time of 4, and then 250. Okay, that means my rise is 20 meters and my run is 1.5 seconds. Go ahead and run this. So 20 divided by 1.5 is roughly about 13.3 meters per second. So there's my slope, which is my speed. Our y-intercept is the initial position of the car. I'm estimating that. And then what we need to do is take the equation v equals delta x over t, and we have to solve it for the predicted final position x. Well, okay. First, I'm going to solve for delta x. So to do that, multiply by t. So delta x equals speed times time. But delta x is the change in position. It's x minus x naught equals b times t. So to find the final position, I need to add my x naught to both sides. And so the final position is going to be v times t, which in my case is going to be 13.3 meters per second, times the time. Now, in my problem, I was given an elapsed time of 59.2 seconds, okay? Put your time in. You see the time cancels. And then I have to add to that my predicted initial position, which for me, it looks like about 198. Okay, so let's put that in our calculator, 13.3 times 59.2. I'm going to add to that 198. And I'm getting a final position of about 985.4, right, meters. I'm going to just go with 985. I'll round to the nearest meter. Okay, so we're going 13.3, 198, and about 985. Okay, let's go check and see how I did. There we go. Got it right. Okay, so hopefully you were able to get it right too. Average versus maximum velocity. In this activity, you will have a car start from rest. It will accelerate to a maximum velocity, and it will stay at that velocity for a bit. Then it will begin to slow down to a stop. From the position time graph, you are to determine the average velocity for the entire graphed interval and then the maximum velocity from the car. Put your name in the program, and let's get started. Remember, use my tutorial as a template or a guide to help you with yours. If you get stuck, follow along piece by piece, but put in your numbers. Okay, we are told to click on the car to start its motor, so you go ahead and do that for your, and in a moment it will generate our graphs. Okay, so the first thing we're going to do in step one is we're going to very carefully sketch our position time graph on that thing. Now, if you have the ability to copy and paste this into Cami, then by all means go ahead and do that. But if you can't, then you're going to have to copy, you're going to have to sketch it just like me. So for my graph, you can see it's at 20 meters up until about 2 seconds, and then it starts to curve. So I'm going to make a dot there. Okay, so I know that's going to be a straight line until that point. And then I can see it starts to curve. Now, it doesn't start to get straight, at least for my graph, until about 5 seconds. About that, about right here. Okay, and then you can see all the way up my graph. It's going to stay straight until about 16 seconds. So 16 seconds and 210 meters. Make a dot on that one. And then you can see I'm finishing up halfway between 230 and 240. So naturally, I would assume that to be probably 235. Right there. So once I make my dots, I can just kind of sketch through the dots to sort of get what the graph's going to look like. So it's going to kind of curve upwards like this. Okay, then it's going to be a straight line between those two dots, and then it's going to curve concave down like this. Okay, so it's not very hard to graph your graph. You just have to, graph a few points and, Now, what I would do is, for a lot of this, I would use the shapes feature rather than the scribble pen so that you can actually draw straight lines in the middle, okay? But anyway, step one, draw a sketch our graph. Step two, we're going to look for and find the average velocity. So the average velocity, which, by the way, the variable for it is v bar, is your total displacement divided by the total time interval. Now, the total displacement is going to be, I'm starting at 20, and I'm ending at, where is that? 230 and a half. Okay, so I'm going to go 230 and a half. Sorry, that's not 230 and a half. That's, yes, it is, 230.5. So 230.5 minus 20. Okay, so we're looking at 210 meters. And the entire time interval you can see down here is 20 seconds. So 210 and a half divided by 20 seconds. We're looking at an average velocity of about 10.5 meters per second, roughly. Now, to find the maximum velocity, that's going to basically be the slope. That's going to be the slope of this part right here. Okay, that's going to be our maximum velocity. So let's find that slope. Now, for me, I would basically find the slope between those two dots right there. That's what I would do. Find the slope between the two dots where it ended the curve at the bottom and began the curve at the top. So for me, that is going to be a rise of, what is that? 100, 10, 20, 30, 40, 50, 60, 70, about 170. And it's a rise of 170 and a run of, looks like 10, 11 seconds, roughly. So we're going to go 170. 170 meters over 11 seconds. and I'm getting a maximum speed of about 15.5 meters per second. Okay, let me put my values in, see how I did. You do the same. Pause the video if you need to. And there you go. Hopefully you were able to get this correct as well. Problem 3, constant velocity graph. You'll be presented with a graph describing one-dimensional motion of an object moving with 3 distinct velocities. You are to find the velocity, including the direction, for each of the following regions. Okay, go ahead and put your name in the program, and let's begin. All right, now the first thing you're going to want to do is sketch your graph as best you can. Since they're all going to be straight lines, choose the shapes figure in Kami instead of the scribble feature so that you can get accurate straight lines, okay? Probably just got to zoom in a little bit to try and estimate. You can see my point is starting a little bit less than 410. So I'm going to make a dot, make a few dots, okay, for landmarks here. So I'm going to start about right there. And you can see I'm going to 13 seconds at just a little bit above 180, maybe like 185, more or less. So I'm at 13 seconds. 185 puts me about right there. Okay. Now we're going to go all the way up to about 21.5 seconds, pretty much exactly at 350. Or 21.5 seconds. Be about roughly there. Okay, now I'm going to start connecting these dots. You do the same. Okay, there's my graph. Now, in order to find, so region 1, 2, and 3, in order to find the velocity for each of these regions, okay, we need to find the slope, okay? The slope is the slope of a position time graph is the velocity. Okay, now if it's a horizontal slope like mine is here, well, that's going to be an object at rest with 0 velocity. If it's a downward slope, it's going to be a negative velocity, meaning the object is moving in the negative direction, left, down, or backwards. If it's an upward slope like mine here, it's going to be a positive slope, which means a positive forward velocity. So an object moving to the right, upward, or forward. Okay, so let's go ahead and I'm going to take some time to find my velocities. You go ahead and take some time to find yours. Okay. Find a couple points where it's crossing through the graph paper almost perfectly. I really like the points at 5. Actually, I could probably do better than that. Let me see. Okay, I like the point at 4 seconds a lot. Didn't really show up that great on my graph, but at 4 seconds and 340. So 4 seconds, 340. And then if I go a little bit further down my graph, I'm liking that point at 8 seconds, 8 and 270. That'll be about right there. Okay. So I'm going to obviously take the difference between 340 and 270 to get my rise. I'm going to take the difference between 8 and 4, which is 4, to get my run. So my rise is going to be 340 minus 270. Well, actually, it's 270 minus 340 to give you a negative value. Okay, so we have a rise of negative 70, a run of 4. Okay, so I'm looking at a speed of negative 17.5. So region 1, we're going to go negative 70 meters over 4 seconds, which is about negative 17.5 meters per second. Okay, region 2. Well, for me, it's going upward. Okay, figure out your slope of region 2. Well, I really like, on my graph, the point that goes right through. Gosh, it seems like every other point. I really like the point at 14 seconds and again at 15 seconds. So these 2 points here, right here and right here, very close together. So that would be a rise of 20 and a run of 1. So that's a slope of 20. All right, and then region 3, that one's easy. It's a flat line for me anyway, so that's going to be 0. Figure out your slope. I want to put my values in the program, see how I did. And there you go. Hopefully you were able to get this question correct as well. Question 4, acceleration from a velocity graph. In this activity, you will have a car start from rest, accelerate to a maximum velocity, stay at that velocity for a bit, and then slow down until it stops. From the velocity graph, you are to determine the acceleration for the car when gaining speed, and then the acceleration while losing speed. Go ahead and enter your name in the program. Let's begin. Click on the car. And you can see now we're generating a velocity time graph. So you can see for the first 3 seconds of my graph, the car wasn't moving. And it's going to accelerate from 3 seconds to 8 seconds, from 0 to 20 meters per second, until about, it looks to be about 20 and a half seconds. And from 20 and a half seconds all the way to 28 seconds, the car slows down to a stop. Well, I want you to take the time to go ahead and graph yours. Go ahead and click on your shapes menu option in Cami and go ahead and graph. So I'm going to go ahead and graph mine, you graph yours. Try to start your graphs by just plotting some dots. That way you know how to connect the lines. Okay. Now that we've got it plotted, to find the acceleration, find the slope of the velocity time graph. Okay, so we're going to find 3 slopes because there's 3 line segments. All right, so A1, now if you look on your graph, A1 is the first colored region over to the left, A2 is the second colored region over to the right. A1 is when the car is speeding up, A2 is when the car is slowing down. So for me, that region is right here. Okay, and A2 is specifically this region here. Okay, so for region 1, that's going to give us A1. So to find A1, I need to find the slope. So I'm going to go up from 0 to 20. So I have a rise of 20 and a run of what looks to be about 5 seconds. So I'm seeing an acceleration of positive 4 meters per second squared. Now, for step 3, we're going to show the slope of this line to find the acceleration when it's slowing down. So for that one, we're losing 20 meters per second, but then let's see, 1, 2, 3, 4, 5, 6, 7.5. Oops, wrong section. So it's going to be negative 70 over 7.5. Negative 20, sorry. Negative 20 over 7.5. Okay, that'd be roughly about negative 2.7. Okay, now the optional question is asking how far did it go when it was moving at top speed. Well, I'm not going to solve that one for you right now because we'll do that a little bit later on in the next problem. But suffice it to say, it would basically be this. If I found the area under the curve, okay, from this area right here, right there, under that rectangular region, because that rectangular region represents what? The maximum speed. So if I find the area under that, I would find out how far you went, right, as a maximum speed. But I'm not going to go ahead and do that now. Let's go ahead and enter. I'm going to enter my values. You enter yours. So for me, it's about 4 and negative 2.7. All right, there we go. Hopefully we were able to get question number 4 correct as well. Question 5. Finding displacement from a velocity graph, level 1. You'll be presented with a velocity time graph describing the one-dimensional motion of an object. You are to find the displacement of the object during the interval depicted in the graph. Okay, go ahead and put your name into the program. Let's begin. So there's 2 things that we learn how to do with velocity time graphs. We saw in the previous lesson is if we find the slope of a velocity time graph, that gives us the acceleration. If we find the area under a velocity time graph, well, that gives us displacement. So that's exactly what we'll do. We're going to find the area under the velocity time graph for region 1, region 2, and then region 3. First thing you should do, this is the first thing I'm going to do, is I'm going to sketch my graph that's shown. They're all going to be horizontal lines. You just have to kind of carefully figure out where they're changing the horizontal status of the line. So everybody take a minute, pause the video, go ahead and get yours together. Okay, so for me, this is region 1, this is region 2, this is region 3. Okay, you should have sketched your graph already. Now, I'm going to go ahead and shade these regions just so I can look at them differently. My first region is a big rectangle. Okay, my second region, right, smaller rectangle. Okay, and my third one, right, a much taller rectangle. Okay, so all of these are rectangles. The area, of course, is base times height, or length times width, whichever you prefer. So find the height for each one of them. I think that's going to be the easy part. The base, okay, is going to be a little bit more involved in some cases. So for me in this first one, you can see I've got a height of 22 and a base of 50. Remember, you can see each mark is going by 10 seconds. So I've got 50 seconds times 22 meters per second gives me about 1,100 meters for the first one, for region one. Okay, region two, got to estimate a little bit because it's going a little bit more than 50. So if I had to estimate here, let's see, this would be 110, that would be 105. So I'm gonna put that at maybe 103 right here, this mark, maybe about 103. So the difference, of course, between 103 and 50 would be 53. So we'll go 53 seconds times 9 meters per second, right? And we're looking at about 477 meters for my second region. And then for this last one, so I'm taking the difference between 200 and 103, right? And that, of course, would be 97. So now I'm going to take 97 seconds on the base times 16 meters per second, and I'm looking at about 1552. Okay. So yeah, you've got to have your region 1, 2, 3. So for region 1, right, the displacement was 22 meters per second times 50 seconds, right? Gave me 1,100 meters. For delta x2, it was 9 meters per second times 53 seconds. That gave me 477 meters, right? And just to finish this recap, delta x3 was 16 meters per second times 97 seconds. And that one gave me about 1,552 meters. Okay. Now, total displacement, of course, would just be delta xt, would be the sum of all these. So we're going to go 1,100 plus 477 plus 1552. All right, and I'm getting about 3129 meters. Let's go ahead and check it. And there you go. Hopefully you were able to get the question right as well. Question number 6, two-stage average versus maximum velocity. In this activity, you will have a car start from rest, accelerate to a maximum velocity, and stay at that velocity for the remainder of the graph time. From the position time graph, you are to determine the average velocity for the entire graphed interval and then the maximum velocity of the car. Go ahead and enter your name and let's begin. Remember, please use my tutorial as a template or guide to help you solve yours. Click on the car to start its motor and your graph will be generated. As you can see, the car is accelerating, so you should be experiencing a curve upwards, but now the car has reached maximum speed and it's going at a constant speed, meaning a straight line for the remainder of the graph. Okay, so the average velocity is found by taking the total displacement divided by the total time. Okay, so the total displacement on there, you can see my car gets to a position of about 180. Started at, not at 0, but it started at a position of a little less than 30, I'll say 29. Okay, and of course the time interval would be 10 seconds for the entire run. Go ahead and calculate yours, I'll calculate mine. And I'm looking at an average of about 15.1 meters per second for my car's average speed. Okay, so now the average velocity takes into account the total displacement and the total time. The maximum velocity, however, is after the car is accelerated to its top speed, which would be the constant velocity or straight part of the graph. So basically what we got to do is find the slope of the straight part of the graph, and you will have the velocity. So my endpoint is around 180. Let's see, another point. It's going to be tough. I'm going to have to do some estimation here on other points. So let's say I just went between those two endpoints right there on 9 and 10 seconds, so a 1 second interval. So at 9 seconds, you can see I'm at 160, maybe 163, something like that. So Vmax, right, which is equal to the slope. And so I'm looking, my coordinate points, I'm looking at about 9 seconds and 163 seconds, I guess that's what I'm estimating, to 10 seconds and what appears to be about 182, which kind of makes me want to go back and revisit my average real quick. So I'm going to make that 182. It's going to affect my calculation slightly, so I'll fix it. So 182 minus 29 divided by 10 seconds. Yeah, it affected it a little bit, so about 15.3. So, but it's the same ballpark. All right, so now to find my rise, I'm just taking the difference between those two numbers. To find my run, it's 1 second. So 182 minus 163, right, is about 19 meters per second, or meters, excuse me, in 1 second, right? And I'm looking at approximately 19 meters per second, right? Well, let's see how close I am to that. 15.3 and 19, let's check it out. All right, there we go. Correct again. Hopefully you were able to get this question correct as well. Next question, graphing time till collision. So what we're going to do in this one is we're going to have Pac-Man, from the game Pac-Man. He's going to be headed to the right, and a ghost is going to be moving to the left. Okay, you will know the starting location and velocity of each. So our job is to use that information, graph it, and see when and where the two will intersect. Put your name in, let's begin. So you can see from my picture here, okay, and remember, use mine as a template to try and figure out your own. But from my picture here, you can see Pac-Man is starting on the 190 millimeter mark. So let's make a note of that, starting at 190 millimeters. The ghost is starting at the 690 millimeter mark. Okay, the initial velocity of the ghost would be 90 millimeters per second, and the speed of Pac-Man is 140 millimeters per second. Now I'm going to make one change. Since Pac-Man's going to the right, he's going to have positive initial velocity. since the ghost is going to the left, he's going to have negative initial velocity. That's going to mean a negative slope. You'll see what I mean when we get to that. So the first thing we're going to do is we're going to plot our y-intercepts. The y-intercepts will be these initial locations. So I'm going to go and do them different colors. So I'm going to make, I'll do black, Pac-Man in black, and I'll do the ghost in blue. Okay, so just choose whatever two colors you want, but color code them. Okay, so now Pac-Man's starting at 190, so I'm going to make a dot here. And he's moving at a rate of 140 millimeters every second. Okay, what that means is that's a rise of 140 over 1. Now you can see that two of these major boxes, not one major box is a half a second. Okay, so two major boxes would be 1 full second. So I'm at 190. So I'm going to kind of just keep going up 140 over 1, 140 over 1. So just keep adding. So I'm at 190. Okay, then I'm going to add 140. So now I'm at 330. So I'm going to go 330 over 1. There's my next dot. From there, I'm going to add another 140. So now I'm up to 470. 470 over 1. And if you do that, you're going to get a nice straight line, right? So just keep doing that. Keep doing that with your slope. Whatever your slope is for Pac-Man, whatever your speed is for Pac-Man, go ahead and plot that. 660 over 1. There we go. Oops, that's a little bit too much. Oh, oops. Boy, I messed that up. Okay. Back that up. 470 plus 140. There we go. 610. That's better. Okay, 610. And then 610 plus 140 is 750. I will end it here. And now when you get your dots, go ahead and click on the shape menu option in Kami and go ahead and draw yourself a nice straight line through that. And that, of course, represents Pac-Man. Okay. Now, switch your colors, okay? My ghost starts at 690. So I'm going to make a plot at 690. And I'm going to go down at a rate of 90 millimeters and then over 1 second. So that would bring me down to 600 over 1. 600 over 1. Let me see. So now I'm down to, so I'm at 510 minus 90. So now I'm at 420 right here, minus 90. Now I'm at 330, 330, just about right there. Okay, so now go ahead and do that. Okay, and now really to finish off this problem, all you're going to do is you're going to estimate as best you can the time of collision, which would be there, and the position where the collision occurs, which would be right there. So I can see the time for my collision is it's almost about 2.2. So I'm going to say 2.19 maybe, 2.19. And then my location to collision is almost 500. I mean, it's almost there. So I'm going to say like 498, something like that. It's going to run the animation, and when they collide, you're going to see how well you did the problem. Okay, and my calculations were close enough to be correct. I hope you were correct as well. Question number 8, instantaneous velocity from graph. In this program, you'll be presented with a graph of position versus time for an object that's gaining speed at a constant rate. In other words, constant acceleration. You will use the tangent line to find the instantaneous velocity at a given moment in time. Go ahead and put your name into the program. Let's get working. All right, now, it's going to ask you, use the arrows below to find the position of the object and the instantaneous velocity at 5.6 seconds. Well, right now you can see it's at 1 second exactly, so I need to move that over. So I'm going to use the big arrow. Now I'm at 2 seconds, 3 seconds, 4 seconds, 5 seconds, Now I'm going to use the smaller arrow. The smaller arrow lets me go 1/10 of a second. So I'm going to go all the way to 5.6, which is exactly right there. See, I'm exactly at 5.6 seconds. Once you get there, then I need you to take a screenshot and paste that graph onto your Google Doc. There we are. Okay, now at this point, we're going to find the position at 5.6, and we're going to find the velocity. Now, the position's easy. We just read that right off the graph. So at 5.6 seconds, you can see I'm going all the way over to the left, and that's about 73 meters. Okay, so that one's pretty easy to read. Now, to find the velocity, okay, so the position, so for me, the position X is 73 meters. The velocity is going to be the slope. So I got to figure out the instantaneous velocity by figuring out the slope. So I'm going to find two very convenient points. I really like this point right there. And I'm going to keep going up the graph till I find another one that I like. I like that point right there. So I'm going to go rise up 9 boxes over run up over 4 boxes. 9 boxes would be exactly 9. 4 boxes would be 0.4. Put that in my calculator. 9 meters over 0.4, 0.4 seconds. And we get 22.5 meters per second at that particular point, okay, for my graph, okay? Make sure you find the slope of the tangent line at your given time for your graph. So let's see how this worked. And there you go. Hopefully you're able to get this question right as well. Okay, last question, number 9. In this one, you're going to be finding the acceleration from 2 instantaneous velocities. So it's going to be like question number 8, where we find the slope of the tangent line to the curve, but we're going to do that at 2 different points. So if we find the instantaneous velocity at 2 points, we can then use change in velocity over time to find the acceleration. So that's going to be our strategy. Go ahead and put your name in the program. Let's begin. Remember to use my tutorial as a template for your attempt on your problem. Okay, so the first thing you're going to do is you're going to lock in 2 different times. For me, my times are 1.1 second and 5.5 seconds. What I want you to do is I want you to lock in both of your times and take 2 screenshots. So I'm going to go ahead and do mine. You take a moment to go ahead and do yours. Okay, there's the first graph. Okay, again, go ahead and get both of your graphs copied and pasted. I need to move mine to 5.5 seconds. All right, so now, hopefully you have yours in there. So now I'm going to go ahead and find my instantaneous velocities at 1.1 seconds and 5.5 seconds, and then I'll throw that into my equation down here. Now keep in mind, delta V over delta T means V minus V naught. Okay, so this is final velocity minus initial velocity. Over T minus T naught. Now, normally T naught would be 0. Well, not in this case. See, this time we're looking at the initial time is, for me, 1.1 seconds. The final time is 5.5 seconds. So your delta T is going to be the difference between your times, okay? Normally T naught is 0, but when you're dealing with a graphing motion problem, sometimes T naught exists in the problem. Okay, so once you find your change in velocities, go ahead and enter them into this, and then divide that by the difference in your times, and you'll have your acceleration. So go ahead and take the time to find the slope of each tangent line to find each of your velocities. All right, I really like the actual point right there. That's a good point. And like this point here, that would make me go up 3 boxes and over. Okay, so 3 boxes on this scale is 3. 1, 2, 3, 4, 5, 6, 7 boxes would be 0.7. So I'd be looking at 3 meters over 0.7 seconds. And that's 4.29 meters per second. So I'm gonna need that. Now that's an answer I have to put in here too, so I'm gonna box or circle it, 4.29, okay. So got that part. And then my second graph, same thing. Don't know that I like that tangent line point. Let me just start at the bottom. Okay, where's a good point? Okay, really like this point here. And I guess that point there, I mean, they're pretty close to each other. That would make me go up 4 boxes and over 2 boxes. Well, going up 4 boxes on my scale is literally 4 meters. Going over 2 boxes would be 0.2. Yes, 0.2. So that would be 4 meters over 0.2 seconds. And we're looking at what, 20 meters per second. So accelerating between that time interval, my object is accelerating from 4.29 meters per second to 20 meters per second. So go ahead and enter that data into your acceleration equation. So we're going to go 20 meters per second, because that's your final velocity, minus 4.29 meters per second over t final, which is 5.5 seconds, minus t initial, which is 1.1 seconds. My change in velocity between that time interval is 15.71 meters per second. My time interval is exactly 5 seconds. No, it's not. Sorry, let me try that again. 5.5 minus 4.4, there we are. My time interval is 4.4 seconds. So my unit is going to be meters per second, which is meters per second squared. So for me, I'm looking at an acceleration of about 3.57 meters per second squared. Go ahead and enter yours into your program. And there you go. Hopefully you were able to get this question correct as well. I hope you found this video tutorial series to be helpful in the assignment called Graphing Problems. Thanks. See you next time.